part 4 of the titration curve. So part 4 is adding 25 milliliters of sodium hydroxide. So I've got my burette, which in it is 0.30 molar sodium hydroxide, and I've got my flask, and in my flask I am starting out with 25 milliliters of weak acid that is 0.30 molar. Okay, so now I am going to add 25 milliliters. So now my total volume is going to be 50 milliliters. 25 milliliters of sodium hydroxide, 25 milliliters of weak acid. I have a total volume of 50 milliliters. Again, before we do anything with volume, we need to calculate the number of moles of everything that's in there to see what is happening with the chemistry. So how many moles of weak acid are in the flask, and then how many moles of sodium hydroxide are in the flask. And then what does this mean for the chemistry? What kind of chemistry is going to happen depending on how much of these different things we have? So the number of moles of weak acid in the flask is not changing. It's the same as step 2 and as step 3. I have 0.0075 moles of HA in this flask, 25 milliliters of a 0.3 molar solution. Okay, how many moles of sodium hydroxide are in the flask? So now I have 0.0250 liters, 25 milliliters, and I still have a 0.30 mole per 1 liter, which gives me 0.0075 moles of sodium hydroxide. Okay, so what is happening here? This is the equivalence point. This is the point where I have equimolar concentrations of acid and base. The 0.075 moles of sodium hydroxide will completely neutralize the weak acid. It will also produce 0.0075 moles of the conjugate base. I'm going to write all of that out. The 0.0075 moles of sodium hydroxide will completely neutralize the 0.0075 moles of HA. So it's gone. No more HA. We've completely neutralized it. But remember, in the neutralization, you also produce the conjugate base and will produce 0.0075 moles of conjugate base. So the sodium hydroxide and the weak acid have totally neutralized each other. So there's none left. So what is affecting the pH? The sodium hydroxide and the weak acid are gone. They have neutralized each other. The only thing in the flask to affect the pH is the conjugate base. That's the only thing impacting the pH in this flask now. because we've added equal molar concentrations of conjugate of a strong base and weak acid. They've totally neutralized each other. But now this 0.0075 moles of conjugate base is the only thing impacting the pH. So how do I solve for pH when I just have a base? Now, this is a weak base ionization. And instead of my equation here, I'm just going to use the generic equation. I'm going to call A minus, the conjugate base, I'm going to call that B. Or I could just call it A minus. I don't mean for this to be confusing. So A minus is the conjugate base. I'm just going to call it B, which is the generic base. Or I could do it this way, but I'm going to do, I'm going to do it this way. I'm going to say, here's my generic base, which is my A minus. And that would be the conjugate acid of my base. So what's so important about these titration curves is that there's different types of chemistry happening at all different spots along the curve. So at this point, at the equivalence point, the strong base that we added, the sodium hydroxide, neutralized all of the weak acid. So there's no sodium hydroxide left to affect the pH. There is no HA, weak acid, left to affect the pH. But what is now in that flask is the conjugate base, the salt that contains the conjugate base that was produced. So if we go all the way back to step 2, when we look at the neutralization, these two totally neutralize each other. And now all that's left in this flask is this weak base ion, this fluoride ion, which is the A minus in my example, or the B, which is the base. So now this is the only thing affecting the pH. So to solve for the pH, I'm going to solve for the hydroxide ion concentration at equilibrium, but then remember to convert it to hydronium or to solve for the POH to get to the pH. Okay, so what is the initial concentration? The initial concentration is not 0.0075 because 0.0075, that is the number of moles, not the concentration. So let's just do this over here. If I have 0.0075 moles of A minus, and I have a new volume of 50 milliliters, or 0.050 liters, that means my concentration is going to be 0.15 molar. So that's my initial concentration, 0.15. Make sure that you don't put the number of moles in the equilibrium table. What goes in the equilibrium table is always the concentration in molarity. So no water, no hydroxide, no conjugate acid. So plus X, 0.15 plus X, this is going to be, that's minus X. Minus X, minus X, plus X, plus X. Okay, so now what do we use to do a weak base ionization? We need the Kb. So remember, we were given the Ka of the HA, the weak acid, to be 6.6 times 10 to the negative fourth. Remember that Ka times Kb equals Kw, which is 1 times 10 to the negative 14th. So if I take 1 times 10 to the negative 14th and I divide by 6.6 times 10 to the negative 4th, 1 times 10 to the negative 14th divided by 6.6 times 10 to the negative 4th, 1.5 times 10 to the negative 11th, this is the Kb that we're going to use for this. I know the assumption principle is going to work here. The ratio of the initial concentration to the Kb is going to be much greater than 500, so I can assume X is negligible. So I'll write this out just so people will know. Kw is 1.0 times 10 to the negative 14th equals Ka times Kb, which is how I got the Kb to solve for Kb using the Ka and the Kw of water. So now I'm going to say Kb 1.5 times 10 to the negative 11th equals x times x squared over 0.15. So I'm going to multiply both sides by 0.15. Take the square root of both sides. So 1.5 times 10 to the negative 11th times 0.15 square root is 1.51 times 10 to the negative 6th. So that's x. 1.51 times 10 to the negative 6th. Remember what x is. X is the hydroxide ion concentration. And I'm solving for pH. So I would say POH equals the negative log of 1.51 times 10 to the negative 6th. 5.82 POH equals 5.82. So that means the pH is 14 minus 5.82. pH equals 8.18. So the pH, after we added 25 milliliters of sodium hydroxide, is 8.18. So the chemistry here at each of these steps is so important. You need to be able to think about molecularly what is happening, what is neutralizing what is left over, what is affecting the pH. So at this point, all of the weak acid is neutralized by all of the strong base, leaving only the conjugate base that is produced during the neutralization to impact the pH. That's why to calculate the pH at this step, we do a weak base ionization. Okay, so after adding 25 milliliters, we are at 8.18. We'll say that's right about here. There's step 3. No, step 4. Where did my step 3 go? One, two, three, 4. Yep, that's 4. I just forgot to write 3. Step 4 is 25 milliliters of NaOH. pH equals 8.18.